Well, thank you for that introduction and welcome everyone. Today, I'm going to be talking about a new age of computing that we've entered, one that's given rise to specialized processors and accelerators, the likes of which we've never seen before. What I'm going to do in this talk today is I'm going to talk about how it is that we got here and how we can continue advancing computing in this new age of accelerators. Moore's law has been a mainstay of the semiconductor industry for many decades, and it's enabled numerous processor and memory innovations that have advanced computing. Originally observed by Gordon Moore in 1965, Moore's law noted that the number of transistors in a chip was doubling about every 2 years. And this relentless progression of Moore's law since the 1960s has been an important tool for our industry, allowing more complex functionality in each chip, as well as integration of those chips to reduce cost and to reduce power. In the span of several decades, the semiconductor industry has gone from manufacturing in microns to manufacturing in just a handful of nanometers, and further improvements are on the horizon. These improvements in manufacturing have enabled today's processors to scale to hundreds of billions of transistors per chip, enabling more functionality at lower cost than ever before. A great example can be seen in PCs. Today's PCs house orders of magnitude more computing power than the early PCs of the 1980s and 1990s. And even more so, it's interesting to note that that's done at a fraction of the cost from the 1980s and 1990s. The semiconductor industry's ability not only to pack more functionality into these chips, but also to reduce cost has in turn led to a proliferation of semiconductor devices. And this proliferation has again allowed the devices to become better connected to each other. And that's enabled new forms of computing paradigms like mobile and cloud computing. Computing paradigms are continuing to evolve as we generate increasing amounts of digital data and as we create new ways to analyze this data and make use of the insights. A great example of the semiconductor industry's ability to improve functionality and reduce cost is the smartphone. These converged mobile devices bring together incredible functionality, things like phones, cameras, messaging, video, music, navigation, calculators, calendars, alarm clocks, and more are all brought together into a single device. Smartphones are so ubiquitous and so powerful that entire categories of devices have largely been replaced, like pagers and music players, thanks to integration and cost reduction that have resulted from Moore's law. Perhaps the most impactful example of the impact that the semiconductor industry has had on our society can be seen in the space program. The computing power NASA used to put a man on the moon in 1969 was packed into the equivalent of only 16,000 transistors. And it's dwarfed by the computing power we can hold in our hand these days. The Apple A15 processor, for example, in the newest iPhones, has 15 billion transistors. And that's an example of the power of semiconductor scaling and the increased functionality that Moore's law has brought us. Chips with billions of transistors have created enormous value for consumers and businesses all around the world. But behind the scenes, the way engineers have designed these chips has had to evolve as well. Increasing numbers of transistors forced changes in the way chips themselves were designed, as the complexity of the chips became increasingly more difficult to manage. Original chip design methods used a flat architecture where the team designing the chip had to design everything themselves in one layer. But as the complexity of a chip grew and as more chips were being created to serve different market needs, it was no longer feasible for teams to design everything themselves and in a flat hierarchy. The solution, as we all know, was the advent of the hierarchical standard cell-based design. Dividing the design into layers and partitioning the design into multiple blocks made the design process much more efficient. Additional advances like graphical design tools and hardware description languages enabled engineers to be more productive as well. Designers can work on the block separately and in parallel, all the way from RTL design through physical implementation, manufacturing, yield reduction, and analysis. And block-level timing closure made it easier compared to having to close timing on an entire chip, all in a flat design. So once all the blocks are finished, they can then be integrated into a final chip, and this hierarchical approach made things much more efficient and much easier to manage. Now, this move towards a hierarchical design really gave birth to a new industry, the IP industry. Now that the semiconductor industry had a way to make design easier and better through the use of functional blocks, more feature-rich silicon could be made, and silicon design really took off. So this new industry that was developed around IP cores was really built around the fact that companies could specialize in designing and selling special blocks that were needed across many different chips. And reusing those blocks made it easier and more cost-effective because they were common elements across many chips. Instead of each company having to design these functions themselves, they could now turn to third-party companies for these features, which again reduced design cost and time to market. An added benefit is that chip companies can now focus their engineering resources on the higher level functions that really differentiate their full chip design from the competition. And third-party companies could begin to specialize in the design of various IP cores that were in high demand and that needed to be instantiated across many different designs. It enabled a stronger focus on performance, power efficiency, and functionality for these cores. IP cores enable the semiconductor industry to innovate faster, to develop chips more quickly, and to mitigate both the increased design complexity of the chips and the cost of designing everything in the chip each time. And as the industry evolves, we're now seeing an extension of the IP cores concept, where collections of IP cores are aggregated together and manufactured into a single small chip called a chiplet. And that chiplet provides a set of common functions that can be reused across systems. We expect further evolution to continue in the future. But after decades of reliable improvement in manufacturing brought to us by Moore's law, our industry finds itself at a very interesting crossroads. As Gordon Moore himself said, no exponential is forever. And today we see that Moore's law is unfortunately slowing. The world has become increasingly dependent on semiconductors. And the irony of all of this is, just at the time that the industry needs it the most, one of its most reliable tools, Moore's law, is no longer available in the form that it once was. The actual semiconductor scaling has fallen off the rate that was originally discussed by Gordon Moore in the 1960s, such that at the turn of the decade, there was about a 15x gap between what was predicted in the 1960s and the actual transistor densities that were available. In addition to Moore's law, the industry has also relied for decades on something called Dennard scaling to reduce chip power. Moore's law and Dennard scaling worked together to ensure that while the number of transistors per chip could reliably increase, each of those transistors could operate at lower power, and that would ensure that the total power on a chip could remain manageable over time. While we've seen the slowing of Moore's law, what makes matters worse is that Dennard scaling, or that scaling and reduction of power, stopped in the mid-2000s. Around the 65 nanometer node, Dennard scaling began to fall apart and is now nowhere near its historical past in terms of the power densities that we're able to achieve. And we've gotten to a point now where the power densities on the chips are dramatically larger than they would have been if we were able to stay on that historic trend. Unfortunately, from the 50 nanometer node till today, power densities have gone up by about a factor of 4, making power and thermals much more limiting in terms of the design and capabilities of our chips. The upshot of the slowing of Moore's law and the end of Dennard scaling has meant a dramatic slowing in the performance of processor cores in recent years. With classic CISC architectures, we got a doubling in performance about every 3.5 years. And that was in somewhat of a heyday for processor design back in the late 80s and early 90s. Around that time, we started to see a shift towards RISC architectures, which gave us a great run of about 2 decades, where we were able to achieve a doubling in performance about every 1.5 years. And we would get dramatic increases in performance. But as we got to the end of Dennard scaling, things started to slow, and we had to move towards new ideas, in this case, multi-core architectures. And the trend in improvement, although it did provide some improvement, it couldn't keep up with the historical trend provided by RISC architectures. Still, we were able to get back to about a doubling of performance every 3.5 years, very similar to what it was in the early days of CISC architectures. But as things really began to slow down, we started to have more trouble in terms of improving the performance of our processing cores. And in recent years, it's dropped to a doubling in performance about every 6 years. And so we're really seeing the impact of the slowing of both Moore's law and the loss of Dennard scaling as it was before. Now, we've pretty much run into a wall where the typical techniques we've used in the past to improve performance, now they only really manage to eke out about a doubling of performance every about 20 years or so. So even our most tried and true brute force methods are failing to deliver at anything close to the historic rates we've seen in the past. So an important question that faces the industry is, how do we get back to that historic trend of improvement that we've seen in the past, something that the industry has come to rely on over the past few decades? Well, there's still an insatiable desire for more performance, and certainly to match those historic trends we've seen in the past. And the industry has turned to a more heterogeneous approach that combines something called domain-specific computing together with accelerators into full systems. The idea here is that domain-specific processors are hyper-optimized for specific functionality, making them less general, but far higher performance and more power efficient than general-purpose CPUs. And by combining a set of more optimized processors together into a system, we can now achieve both higher performance and better power efficiency than we can using the traditional brute force techniques that are slowing because of the slowdown of Moore's law and the loss of Dennard scaling. Today, we see a proliferation of purpose-built computing devices. We see GPUs, DPUs, NPUs for networks, infrastructure processing units or IPUs, and application-specific acceleration processors, APUs. They're all implemented as SoCs, and increasingly, we're also seeing the adoption of very powerful FPGAs as well in places like the data center. As system architectures evolve to include more processors, one of the new challenges we're seeing is that it's increasingly difficult to move data quickly and efficiently between each of these processors so that the data can be processed in a timely and power-efficient manner. Closely related to this problem is the need for securing the data as it moves around the system between chips. And this is opening a bunch of new needs that we're seeing in systems as the system architectures themselves evolve. Now, one great example of the need for increasing security was seen in one of the older iPhone models, the iPhone 5S, where Qualcomm used a security IP core in the Snapdragon processor. This was one of the big realizations that security was becoming a growing need for these kinds of systems. And as we've seen in the years since, security demands have only grown in both mobile computing as well as the data center. Well, what's really driving a lot of the change in architectures that we're seeing in both mobile computing and the data center? It's really pervasive connectivity and the amount of digital data in the world that's driving the way that things are really changing. So the pervasive connectivity, for example, it continues to drive evolution in the ways that we both create and digest information. And domain-specific processing techniques are growing in importance because of the importance of the way we create and digest this information. This slide illustrates just how important data is in the form of content and analytics to our lives. It's a nice graphic that shows every minute of the day how different services that we're all very familiar with create and consume data and how it's moved around as well. So for example, just to highlight a few of the things in this slide, every minute of the day, Google conducts 5.7 million searches. TikTok users watch 167 million videos. Netflix users stream almost 500,000 hours of video, and Amazon consumers spend a little more than $250,000 every minute. So not only is serving and moving all of this content extremely important, but we're seeing that analytics performed on this data and user behavior is becoming increasingly important as well to the success of businesses. And what makes this particularly challenging is that moving data is somewhat of a bottleneck in systems. It costs a lot of power and it takes a lot of time. And not only do you have to serve and move that data to provide users with a good experience, you also have to serve and move and analyze that data in AI and machine learning type analytics algorithms to make your services better. So we see two tremendous needs here, all related to the tremendous growth in the amount of digital data in the world. And the amount of digital data growth is really astounding. And this is one of many different studies on the topic. And really, what's surprising about it is that even by the most conservative estimates that are out there, the world's digital data has been doubling about every 2 to 3 years. And with a growing need to process that data as quickly as possible, what we've seen is that people are turning to techniques like AI because it's really one of the only reasonable ways to make sense of all of this data in a timely fashion. And what makes this even more challenging is that for things like search engines, we've grown accustomed to getting an answer in under a second. If the amount of data we have to search through continues to grow at this type of rate, it becomes harder and harder to sift through it all and try and deliver an answer in the same amount of time. But this is an illustration of one of the important challenges that the semiconductor industry is faced with. And that's how to continue moving and analyzing growing amounts of data in a timely fashion to meet the needs of users and businesses. So I'm going to spend some time talking about how AI has evolved and become as important as it is today. It's a great example of where domain-specific processing has helped to improve computing capabilities and the types of services and experiences that can be delivered to end users and businesses. As I mentioned before, AI is going to continue to be important moving forward, in large part because it's the only reasonable way that we have to make sense of all the dynamic and growing data that's being produced in the world. What's really surprising is that many of the basic techniques around modern neural networks and machine learning have been around since the 1980s. Back then, hardware really wasn't powerful enough to be able to run those algorithms in the way that they're run today. And so back in that time frame, more traditional approaches were used on more general purpose CPUs. But if you fast forward a couple of decades to about 10 years ago, what we saw was that the processing capabilities of chips improved by about 5 orders of magnitude, and memory improved by about 3 to 4 orders of magnitude. And so much so that that allowed neural networks to become much faster than the traditional approaches. And that's really when neural networks and machine learning took off into its current age of adoption. And since that time, domain-specific approaches have been used by many different AI engines. Not only are those engines processing the data more quickly using neural network techniques, we're also grouping together many engines to run problems in parallel. And that combination of having domain-specific programming capabilities that allow an individual chip to run much faster, along with the aggregation of multiple chips together into much larger systems, has given us tremendous growth in the ability of neural networks to learn more complex tasks. From about 2012 to 2018, the ability of AI models to learn more complex tasks grew by an astounding 300,000 times, or a doubling of roughly every 3.5 months. That's far faster than the traditional growth rate predicted by Moore's law, which was a doubling about every 2 years. So it's a phenomenal achievement by the semiconductor industry, not only to be able to improve the processing capability of an individual chip through very specific, targeted, hyper-optimized architecture, but also by being able to chain together multiple of these engines to solve very large and very complex problems. So one of the most interesting things about neural networks used in AI and machine learning is that it basically flips the traditional programming paradigm on its head. In classical programming, a programmer encodes an algorithm and some data together. And the algorithm forms the rules by which the data is going to be processed and by which meaning is extracted from that data. What comes out is an answer that we're looking for. So, for example, if we're writing a program that's playing chess, we write as an algorithm rules for the computer to understand how the pieces move, and some things like goals we're trying to achieve, like trying to capture the pieces, get a more dominant board position, and eventually winning the game. It turns out, though, that many problems are difficult to describe or have rules that aren't necessarily always so clear. So, for example, if we're looking at images, it's easy to tell what makes a bird different from something like a dog. The bird has wings, a beak, those kinds of things. But it's less clear on the surface what exactly makes a dog different from a cat. Both have 4 legs, tails, and fur, but there are things about the structure of the bodies that you can use as clues to tell the difference between cats and dogs. Now, as we try and make sense of the world's data, writing algorithms can be extremely difficult and extremely complex, and it's very hard to articulate the rules in a way that you can get very high accuracy on certain tasks, especially like classification and natural language processing. With AI, we actually address this by turning things around. And the way that AI models work is we provide the AI model with some input data in the form of examples of the things we want it to identify and the answers we're looking for. What the AI model does is begins to configure itself by taking a look at the input examples that it's given and the answers of what those things represent. For example, we might give it a whole bunch of pictures of dogs, cats, and birds. And the AI engine itself will begin to configure itself based on those inputs to understand what the most important features are in each of those images that distinguishes birds from cats and from dogs. What comes out after this process of training a neural network are an internal configuration that formed a set of rules by which the neural network will then classify images that it's never seen before. And once the neural network has configured itself so that it has a high enough accuracy on the training set, it's now capable of being put into the field to take a look at examples it's never seen before and to infer results on this new information. So for example, we can give a bunch of pictures of ice cream cones to train a neural network on what an ice cream cone is. And if it's trained well enough, it can then take a new image like this young girl with this very, very large and tasty looking ice cream cone, and it can identify that this is an ice cream cone because it's generalized based on the examples it's seen during the training set. Now, the quality and accuracy of the identification process really depends on the number of examples that are shown to the neural network and the completeness of that training data. So, for example, if we go back to cats and dogs, have we shown examples of pictures of different breeds of cats and dogs? And have we shown them at different angles and different orientations so that the neural network can generalize about what is a cat and what is a dog? Another thing that matters a lot is the size of the neural network. So a neural network that is larger and can handle more parameters can encode more meaning from the various classifications of images that it's trying to identify. And if we want the neural network to be able to identify more classes of images, having a larger neural network is again helpful because those parameters act as a form of memory that through which we can store information about each of the classes of information that we're trying to identify. Well, if we take a look at some of the more common problems that we see neural networks being applied to today, natural language processing is by far one of the most challenging and complex tasks that neural networks are used for today. And since domain-specific AI hardware has been in use, the size of these neural networks used for the most difficult problems, like natural language processing, has grown by about 10x per year. And in recent years, in 2019, Microsoft's Turing NLG engine, it consisted of about 17 billion parameters. And just a year later, OpenAI's GPT-3 neural network went 10 times larger to 175 billion parameters. And just a year after that, last summer, the Beijing Academy of AI introduced the WuDao 2.0, which crossed the trillion parameter landmark. And there's really no end in sight. There's people talking about 10 trillion model parameters and even larger. And so we look for continued growth in this area as well. Now, as you might imagine, when you start having neural networks that are that large, that have that many parameters, you also need very large and very rich training sets as well. So in addition to the growth of the neural networks themselves, we've seen a growth in the training sets as well. And it's only really through, again, these domain-specific processors and massive parallelism that we've been able to achieve the rate of improvement that we have on these much larger models. And again, what it speaks to is really what's needed by the semiconductor industry to process the tremendous amount of growing digital data in the world. All of this flows down to things like memory and interconnects that are provided by the industry. And especially in the case of digital data in the world, memory is a critical component of AI and all other processing engines. These new challenges, primarily around the amount of digital data in the world and being able to process it and move it as quickly as possible from the memory to processors and between processing elements through interconnects, are all presenting increasing challenges to the semiconductor industry. Here, I'm going to talk a bit about what some of the challenges are, especially for memory. What we find is that there's new challenges arising in memory, and it's an exciting time now because there's actually a number of interesting architectural changes that are going on in the memory industry to meet the growing and insatiable demand for a more data capacity and being able to move that data more quickly. The first is the transition to the next generation of DDR memory that's used in servers and PCs called DDR5. DDR5 provides higher capacities and higher bandwidths compared to its predecessor, DDR4. And it also brings about lower power in doing so. So it helps to address some of the challenges that I've talked about earlier about the need for higher performance and the need to be more power efficient. And we look forward to the ramp up of DDR5 soon in the next generation of processors. But beyond just the traditional kinds of memory that we've grown used to over the last few decades, like DDR, there's a new kind of interconnect that's being introduced called the Compute Express Link, or CXL. This new link is very interesting because it allows us to connect other processors to a CPU through the Compute Express Link, but it also allows us to connect additional memory on those links in different form factors than the traditional DIMM modules. Now, if we go back to the panel on the left, we see a classic server, a two-socket CPU server where the only memory that you can have connected to those processors is on traditional DIMM sockets, which are directly connected to those CPUs. What CXL allows is it allows not only for us to have that traditional memory on those DIMM sockets, but we can add even more memory on the CXL links. And that allows us to expand the bandwidth and the capacity through memory that's going into and out of these processors to levels that are higher than you can get today. And the reason for doing this is really what I mentioned earlier. It turns out that there's a growing number of applications that have to process larger and larger amounts of data and that require that data to be processed and moved much more quickly than before. And being able to expand our capacity and our bandwidth through CXL links is an added bonus for the industry and something that we again look forward to being deployed in the next generation of processors. And CXL itself is an enabler for another direction that the industry wants to move to a little bit further down the road. And this is called data center disaggregation or resource disaggregation. The idea here is that current servers today take some fixed amount of resources like compute, memory, disk, and network, and they put it all into one chassis. And that ratio of these resources can't really be changed. So if you have a workload that doesn't quite need all of the memory capacity or doesn't quite need all of the compute capacity, you end up stuck, and it's not a great balance of the resource utilization to the needs of the application. What data center disaggregation promises is the ability to take these individual resources like compute, memory, storage, and accelerators, and to put them into their own boxes, their own pools of resources. And when a task comes in that needs to be worked on, the task will then go to each of these pools and grab just as many resources as it needs. So a task that needs more compute resources than another can actually grab more compute resources out of the resource pool. And you might have a different task that requires a lot of memory resources, more than the average. And so it can then take more memory resources as needed. And when these tasks are done, those resources can then be returned to these resource pools so they can be provisioned again later to future jobs. The idea here is that you'll have a much better capability to match resource utilization to the jobs that come in. And because these resources are in pools, it also allows you to run more demanding jobs than you could with the traditional server architectures that you see today, where a fixed amount of resources are held captively in one chassis. As we move from left to right, what's very interesting about all of this is that these capabilities, the move to the new generation of DDR memory through to CXL memory expansion, and finally the move towards data center disaggregation. All of these technologies increase the bandwidth and the capacity and the efficiency that's available to compute tasks. And this is a big plus for our industry and something that we look very much forward to as the industry continues to evolve. But one thing that also becomes increasingly important as we start to move towards less tightly coupled resources and to disaggregation of those resources is the need for increased security, the ability to ensure that a job is really authorized to use the various resources, and that we can ensure that the resources, the infrastructure, and the data stay safe is growing in importance. We've all seen that there are a growing number of security breaches, things like Spectre and Meltdown, and many of the new other types of breaches that have been documented. And this growing awareness and the growing need for more security is amplified as we move from left to right on the various technologies shown here. Well, this brings me to the end of my talk here. And what I really wanted to just kind of summarize is that it's an exciting time for the semiconductor industry as we continue to innovate to meet the growing processing, memory, interconnect, and security demands of users. There's a lot of really interesting new innovations like domain-specific processing that'll be needed in the future in order to continue growth in this new era of computing that we find ourselves in. At Rambus, we're proud to have played a leadership role over the past 30 years in improving memory and processing and in developing and advancing the IP industry. And we look forward to continuing to make data faster and safer to meet the needs of consumers and the industry in years to come. Thank you very much.